In this video, we're going to introduce the concept of a function. Let's start with its definition. A function f from a set D to a set E is a correspondence that assigns to each element x of D exactly one element y of E. Kind of nerdy, pretty verbose. Let's go through it a little bit. We're giving the function a name. We're calling it f, and that's a common name for functions. It's probably the most common name. And what we're saying is a function makes a correspondence, a rule, that assigns each element of one set exactly one element in another set. And that's an important part of this definition. When a function pairs values from the first set with values from the second set, it does it in such a way that each element of the first set is paired with exactly one element of the second set. The reverse of that is not true. You can have many different elements of the first set all go to the same element of the second set. But each element in the first set has one correspondence, one value that it's paired with. Rather than saying first set, second set, we have names for these things. The set D that you're starting from is called the domain of the function, and the set E that you're mapping to is called the range of the function. So the correspondence is set up that each element of the domain has exactly one element in the range that it corresponds to. We have a notation for this correspondence for how that assignment's been made. We call it function notation. If the function f assigns the output b to the input a, we write this notation where first we write the name of the function, then in parentheses we write the input, and we set that equal to the output. We read this f of a equals b. Here a is an element of the domain and b is an element of the range. Rather than having to draw a picture to show the correspondence or say it in words that the value a corresponds to the value b, we use this shorthand notation, function notation, f of a equals b. One place where we use this notation is when we're evaluating a function. To evaluate a function means to show what output corresponds to a particular input. So I have an example function here. F of x is the function x squared minus x plus 2. So this is like the mathematical rule that we apply to get the correspondence. It tells us if you know the input is x, the output can be found by following this mathematical rule. The line underneath it is asking us to determine what f of negative 3 is. We need to determine the output that corresponds to the input negative 3. Negative 3 is an element of the domain. We're to find the corresponding element of the range that negative 3 gets mapped to by this rule. Since negative 3 took the place of x on the left side, to get the corresponding output for negative 3, we replace each x on the right side with negative 3. So this becomes negative 3 squared minus negative 3 plus 2. Note the parentheses around negative 3 in the first spot indicating that we're squaring negative 3. Those aren't just for show. We need that there. Negative 3 squared is 9. Minus negative 3 becomes plus 3. Nothing happens to the constant term. We add all those numbers together and we get 14. You don't have to rewrite this, but just to cut out all of the work, we're writing that f of negative 3 equals 14, which indicates that the input negative 3 is paired with the output 14 by this rule, by this function. I'm confident you've seen examples like that before, so I don't want to do too many of those. I do want to show you, however, that we don't have to evaluate a function at a numerical value. We can evaluate a function at an expression. I've got a simple example here, f of a. Well, we're going to follow the same logic we did in the last one. Since a replaced the x on the left side, we're going to replace each x on the right side with an a, and we get a squared minus a plus 2. All that really seemed to do is change the symbol that we were using for the unknown, and you're right, essentially that's what it is. But I use this to build up the next example. F of a plus h means replace the x with a plus h. A common mistake I see is that people attach an h to the end. If that's all I wanted you to do, that would be f of a plus h, the previous line plus an h. But that's not what this says. This says evaluate f at the input a plus h. We're going to follow the same logic we had for the previous two examples. F of negative 3, we replaced each x with a negative 3. F of a, we replaced each x with an a. F of a plus h, I replace each x with an a plus h. Don't change the rule. Here there's some algebra we can do. The square of a plus h is a squared plus 2ah plus h squared if you use the FOIL process. We can distribute a negative through here and get minus a minus h, and then plus 2. None of those are like terms, and so we would stop here. I want you to notice that that's not when you get when you just tack an h onto the end. That's something different. And if this looks contrived, well, we're going to be using this idea later on, and it pops up quite a bit in calculus as well. I want to do another example of evaluating functions just to talk about another issue that could come up. Here the function is written as a quotient, g of x equals 3 over x minus 2. First I ask for g of 1. See if you can evaluate g of 1, the output that corresponds to the input 1 for the function g. To get that, I replace the x with a 1, and then we simplify, and we get that g of 1 equals negative 3. So an input of 1 corresponds to an output of negative 3 for this function. G of 2 is a problem. 2 is not in the domain of this function. If we attempted to plug 2 into this function, we get an expression that is undefined. So we say that g of 2 is undefined, and therefore 2 is not in the domain of g. It's not an allowable input. It isn't paired with anything. Oh, one last thing here. Notice that I didn't write g of 2 equals undefined. It's not equal to anything. That's the whole point. It's certainly not equal to a word. So don't write g of 2 equals undefined. We just write that g of 2 is undefined. These last two examples are just to distinguish between different notations. G of the opposite of a means replace the input x with the opposite of a. So instead of 3 over x minus 2, we get 3 over the opposite of a minus 2. And I guess this can be simplified. We can factor a negative 1 out of the denominator and rewrite this as the negation of the fraction 3 over a plus 2. I only do that to compare that with the answer to the next one. This says find the negation of g of a. This doesn't say plug the negation of a in for x. This says plug a in for x and then negate the entire expression. Notice that that's not equal to what we started with. Again, these examples look contrived, but later on we're going to see that we compare these evaluations to see if a function is what we call an odd function. Here these two expressions came out different, so this function is not an odd function. Odd functions have a special type of symmetry, and it's nice to know if functions are odd when you're trying to graph them or for other techniques. And so this is a comparison we're going to have to make, so I thought I would give an example of it now. G of the opposite of a means plug opposite of a in for the input variable. The opposite of g of a says plug a in and then take the negation of the entire function. Two different things. So that's how you evaluate a function, whether it be at a numerical input or at an expression. Why would you evaluate a function? Well, one reason to evaluate a function is to come up with its graph. The graph of a function f is the graph of the equation y equals f of x. So if we were graphing that first example, f of x equals x squared minus x plus 2, we know that when x is negative 3, y is 14, that would correspond to the point negative 3 comma 14 on the graph. We could get a few more points by picking some other inputs and get the graph of that function. So graph of a function is found by pairing each input with its corresponding output. We plot those locations, we look for the pattern, and we draw the curve or line that connects those points. One thing that must be true of the graph of a function is that it has to satisfy the so-called vertical line test. The vertical line test tells us that in the graph of a function there can be no vertical line which intersects the graph at more than one point. And the reason for that is because of our definition of a function. Each x value gets paired with exactly one y value. If a vertical line touches the graph at more than one point, then that x value is corresponding to 2 or more y values, and that's not allowed in a function. Let me show you some examples of some graphs that aren't functions. The equation of a circle is not a function. How do I know that? Well, I can try this vertical line test. Look at the vertical line formed by the y-axis here. It touches the graph at 2 distinct points. That means that the x-coordinate there, which is 0, has been paired with a y-coordinate at the top and a different y-coordinate at the bottom. That's not allowed in a function. If a vertical line touches the graph at more than one spot, then the x value on that vertical line has been paired with more than one y value. That can't happen in a function. None of these examples are functions. This parabola that's opening to the left fails the vertical line test. This broken graph with the jump discontinuity just barely fails. There's one vertical line that messes this up. If I draw the vertical line through these 2 points right here, that x value has been paired with 2 distinct y values. That's not allowed in a function. If one of those was opened so that that point wasn't included, then this would pass. And then the last example is a vertical line, which fails the vertical line test horribly, because if I draw the vertical line right over the top of it, there will be infinitely many y values paired with one x value. That's not allowed in a function. The graph of a function has to be such that each vertical line touches the graph in at most one point. So a line with a slant to it will pass the vertical line. If you imagine every possible vertical line, each will touch the graph in exactly one spot. Same with this parabola that opens downward. Now that it's not opening sideways, it will pass the vertical line test. This lumpy, bumpy polynomial here will pass the vertical line test. This broken graph passes the vertical line test because on the pieces we can see each vertical line touches the graph exactly once. And then the line down the center doesn't touch the graph at all. There appears to be a vertical asymptote there. That's okay. The vertical line test doesn't say that every vertical line touches the graph exactly once. It just says that there's no vertical line that touches it more than once. Horizontal lines pass the vertical line test. You can tell whether or not a graph is a function just by applying this vertical line test. There's a visual test that you can apply. I bring this up because when we're graphing functions later, you should make sure that your graph passes the vertical line test. If it doesn't, then you know something's wrong. If we have the graph of a function, then determining its domain and range isn't that difficult. The domain of a function is the set of x coordinates for all points on its graph. The range of a function is a set of y coordinates for all points on its graph. So the domain corresponds to the x coordinates and the range corresponds to the y coordinates. If you have the graph of the function in front of you, then you can determine those things just by sight. So in our first example, we have this parabola that opens upward. The domain of the function that gave us this graph is the set of x coordinates on the graph of this function. You have to think x, which is left to right. So how far to the left does this graph extend? Well, this arrow tells us that the graph will be moving forever and ever to the left. Now I know it's moving up, but right now we're talking about domain, which means we're moving to the left. So there's no lower bound. You can go as far to the left as you want. We get all of these points that have been graphed here, and then this arrow indicates that the graph's going to be moving forever and ever to the right. So there's no upper bound either. The domain is all real numbers, the interval from negative infinity to infinity. There are no breaks in the graph where you skip over an x-coordinate. However, the range is restricted. The range is represented by the y-coordinates, and there's a lowest point on the graph. Therefore, there's a smallest element of the range. The smallest possible y-coordinate is -3. And because that y-coordinate is obtainable, there's a point whose y-coordinate is -3, we would put a bracket on that to say that we actually can get that value. You can also get any value greater than -3. You can see that on this branch or on this branch. It kind of doubles up. So the range extends from -3 to infinity. Another way to think of this is to imagine smashing the graph onto the x-axis and asking where the graph would sit. If we were to smash this parabola onto the x-axis, it would cover the entire x-axis because both ends extend infinitely to the left and to the right. So the domain goes from -infinity to infinity. But the range is restricted. If we were to take this graph and smash it onto the y-axis, the lowest point would be at -3, and then the graph would shoot up from there. So it would go from -3 to infinity. In this second example, which we'll see later is based on a square root function, we have a restriction in the domain and the range. Domain is x-coordinates, so how far to the left, how far to the right. Well, the arrow seems to indicate that this graph will be moving forever and ever to the left. There's no lower bound. But there definitely is a largest y-coordinate. The graph just seems to abruptly stop when x equals 5. And there really is a point whose x-coordinate is 5, so we would include it. Again, I want you to imagine smashing that graph down onto the x-axis. Where would it sit? Well, it would cover the number line up into the point where x equals 5, and then it stops. For the range, we look at y-coordinates. So imagine smashing it onto the y-axis, or just follow the graph. There's a very lowest point whose y-coordinate is 0. There is no highest point. This graph will be moving up forever and ever and ever. Let's look at a couple more examples. In the example on the left, you can see the graph is broken. It has a discontinuity. I've drawn in these dashes here to indicate where the function is kind of leveling off in each spot. For the domain, we're looking at x coordinates, and this graph goes forever and ever to the left. And then as you get closer and closer to this spot where x equals 1, the graph looks like it's bending not to touch. This is another asymptote. So the function goes as close to 1 as you want, like you could get 0.9 and 0.99 and 0.99999, but you can't actually obtain a value of 1 because the graph is bending away from that. So we can't include 1. And then the graph starts just to the right of 1. You can get arbitrarily close to 1 on the high side. And then the graph goes forever and ever to the right from there. Domain is left to right. So the domain is the set of all real numbers except for 1. I've written it in interval notation, but another way to write that is just say all real numbers except for 1. And if you want to be math cool, not real world cool, but math cool, instead of writing real numbers, you'll say all reals. That's how the nerds know that you're in the club. You say reals instead of real numbers. So all reals except for 1. That's two different ways of expressing the same answer for the domain. For the range, well, I can see we can go as low as we want. There's no lower bound. This branch goes down forever and ever. And that branch covers all negative numbers, but it levels off before we get to 0. The graph never actually touches the x-axis. So we get up to 0, not including 0. There's no point on the axis. And then the other branch seems to take over on the opposite side of the axis. So it starts just above 0 and goes forever and ever up. This branch goes up as high as you want. That's all real numbers except for 0, and again, if you want to be math cool, you'd say all reals except for 0. See if you can do this last example. Be careful with your notation. Okay, imagine smashing that graph onto the x-axis. How far would it extend? Well, the left end would stop at -2, and there really would be a point at -2 because of the closed dot. The right edge goes over to 4, but there's not actually a point at x equals 4, so we wouldn't include that in the domain. For the range, I want you to imagine smashing the graph onto the y-axis. The graph would start as low as -4, but not including -4. There's no point at y equals -4. There's an open circle. And then the graph covers all y coordinates as high as 3. I know this left edge is down at 2, but remember, when you're talking about the range, you're talking about y coordinates, and the largest y coordinate is all the way up at 3. This is why it's nice to visualize it being smashed onto the axis. If we smash the graph onto the y-axis, the points would extend from as low as -4, not including -4, and as high as 3, including 3. So there are some examples of determining the domain and range given the graph. If nothing else, I hope this helps you understand what domain and range are. More commonly, we're going to need to determine the domain of a function without its graph. In this video, we're going to look at 3 scenarios: finding the domain of a polynomial, finding the domain of what we call a rational function, and finding the domain of a function with a square root in it. The domain of a polynomial is all real numbers. So I've given some examples of polynomials here. You have to remember that the domain is essentially the set of allowable inputs. A polynomial doesn't have any square roots. It doesn't have any fractions with variables in the denominator. All of the terms have variables with non-negative exponents. And so you can plug in any number that you want. Like, even look at my most obnoxious example at the bottom here. It doesn't matter what x is. You can raise any number you want to the 7th power. You can raise any number you want to the 5th power, multiply it by -6. There's no restriction on what you can plug in for x. And so when you have a polynomial, the domain is just automatically all real numbers. So polynomials are covered. Let's look at another example. Suppose we have a function that's written as the quotient of 2 polynomials. Later we'll learn that these are called rational functions, but I'm cheating a little bit by bringing this up now. So we'll just say it's the quotient of 2 polynomials. In the example function here, I've got this polynomial in the numerator and this polynomial in the denominator. Well, since that fraction bar represents division, we know that the denominator can't be 0. Those are the only numbers that would not be in the domain of this function. The domain of this function is the set of real numbers which do not make the divisor, the denominator, 0. The way that I like to do this is to start by finding the excluded values, and I find the excluded values by setting the denominator equal to 0. The one thing we can't have is the denominator coming out to 0. Well, that's a quadratic equation, so I solve that. I would factor, set each factor equal to 0 and solve. We get x equals 8 or x equals -5. And that's the answer, right? No. Those are the two numbers that we cannot plug into this function. The domain of this function is the set of all real numbers except for those. You can plug in any number you want as long as it doesn't make the denominator 0. What two numbers make the denominator 0? 8 and -5. Therefore, the domain is the set of all real numbers except for 8 and -5. Now you'll notice I didn't write this one in interval notation. Interval notation can be a little bit obnoxious when you have multiple excluded values. I'll show you what it would be for this example, but I want you to know that it'd be perfectly okay with you just writing it in words like we did here. But here's the interval notation. As you can see, I had to be careful to reorder everything. I can't write the interval from -infinity to 8 because that would include -5. So my first interval would go from -infinity to -5, and then I'd have a second open interval from -5 to 8. That's how we skipped over -5. And then I'd have a third open interval from 8 to infinity. That's how I skip over 8. I would rather just see you write it in words. That tells the story. I can see that you understand that there are two numbers you can't plug in. When we start graphing these functions later in the course, determining these domain restrictions is going to help us figure out where there are breaks in the graph. It turns out that this graph has two vertical asymptotes, and those vertical asymptotes happen to be the lines x equals 8 and x equals -5. So that's where we'll be using this in the future. The third case we're going to investigate in this video is when you've got a polynomial under a radical. And we'll do a couple of examples of this. So the domain of a function expressed as the square root of a polynomial is a set of all inputs which make the polynomial non-negative. Now, why do we have that restriction? Well, remember that if we expect to get a real number output, the thing under the radical is not allowed to be negative. So the thing under the radical must be non-negative. So to find the domain of this function, I'm going to ask where this radicand is not negative, where it's greater than or equal to 0. This is a linear inequality, and so I can just solve for x. I add 6 to both sides, I divide by 2, and I get that x is greater than or equal to 3, and so my domain is the interval from 3 to infinity, including 3. It's okay to have 0 under the radical. The square root of 0 is 0. That's fine. It would be okay to write this one in words as well. That's fine. You could just write the set of all real numbers greater than or equal to 3. Here the interval notation is nice and concise. That's how I would write it. I wanted to do one more example of this because if the polynomial under the radical isn't linear, then you have to be careful about solving the inequality. Here we're to find the domain of the function f of x equals the square root of 36 minus x squared. How do we determine that domain algebraically? Well, we know the thing under the radical has to be non-negative, so I know that 36 minus x squared must be greater than or equal to 0. Then we factor. This is 6 plus x times 6 minus x. Then we make a sign chart. We know that the two numbers that make this equal to 0 are -6 and +6. And we pick test points. If I plug in this number smaller than -6, then the first factor is negative and the second factor is positive. So this stretch would be negative, and we know that we're not allowed to plug negative numbers in. So numbers less than -6 are not in the domain. If we were to plug in something between -6 and 6, like 0, both factors wind up positive. If you pick a number bigger than 6, the first factor is positive, but the second factor is negative, so numbers bigger than 6 are not okay. So it looks like the domain is just restricted to numbers between -6 and 6 inclusive. It's okay to plug in -6, and it's okay to plug in 6 because it gives us 0 under the radical. That's fine. You can have 0 under a radical as long as that radical is not in the denominator. We know that this is the upper half of the circle of radius 6 centered about the origin, and we would get this graph. Imagine smashing that down onto the x-axis to find the domain. Where does it extend? Well, it extends from -6 to +6. Okay, so we reviewed the definition of a function. We talked about evaluating functions not only at specific numbers but also at expressions. And then we talked about domain and range. If you have questions about any of these topics, don't be afraid to reach out. You can see me in an office hour or shoot me an email.